Hi, welcome back to the Network Plus Certification video series. I'm Mike Redmond, Master Trainer, here to help guide you through your successful journey of becoming a Network Plus certified technician. We're going to walk through a wide variety of topics, starting with basic network concepts all the way through network management and security. In this segment, we're going to take a look at the wonderful world of routing. I'll explain how routers work, describe dynamic routing technologies, and show you how to install and configure a router successfully. First, let's take a look at how routers work. A router is a piece of hardware and inside a piece of software. It forwards packets based on a destination IP address. They operate at layer 3 of the OSI model. So routers come in two different flavors. You have your commercial grade router and your home router. Your home router is usually what you're first exposed to. It's what connects your home PC to your commercial ISP. So at their heart, all routers simply join two or more networks together. We call those subnets or LANs. These networks could be your local LAN or they could be a WAN, such as the internet. However, the router's job still remains the same, to simply send packets to the proper destination. They do this by routing tables. The router strips off its layer 2 information and then it drops IP packets into the queue. The source address at that point is not important anymore. Then your router inspects the destination IP and then the router sends the IP packet out the correct port. This is what the routing table tells the router to do. So you remember our friend Nick. His job is to inspect the incoming packets. First, he strips off all the layer 2 information and drops them into a common queue. So your basic home router has 2 ports. Each row in the table defines a single route, and then each column will identify a specific criteria, like the destination IP or the subnet mask. If the packet's network ID matches the destination LAN IP, the router uses other information to determine where to send it. Next, in the third and fourth columns, we deal with the gateway. It's the IP address for the next hop on the route. We'll get to hops later. And then the actual interface tells the router which port to use, whether to use the LAN port or the WAN port. So it really is all about decisions. First, the router compares the destination IP address to every listing in its routing table, then makes a decision. So it's important to understand that every router, with 2 exceptions or so, has what's called a default route. Usually you'll see listed as all zeros. The router sends incoming packets to a default route unless another line gives it another route. Now, let's say the destination LAN IP is 10.12.14.0 with a subnet mask of 255.255.255.0. The gateway, again, it's usually listed as all zeros, isn't important because it knows its destination IP. So at this point, the router will make a decision that it needs to use its LAN port. Let's take a look at another example. Let's say the destination IP is 76.30.4.0 and it has a subnet mask of 255.255.254.0 or /23. Again, it will have a quad 0 gateway. The router knows the destination IP address. In this case, it knows to send it out its WAN port. So here's what that routing table would look like. A destination IP of 10.12.14.0 with the subnet mask of 255.255.255.0 and a default route of quad 0. The router knows the destination IP, so it will send it out its LAN port. And then in our second example, it knows the destination IP of 76.30.4.0 with a subnet mask of 255.255.254.0, a default gateway of quad 0, and it knows to send it out its WAN port. The last entry, which we haven't spoken about yet, is if the router does not know the destination IP. It would come in, for instance, its default gateway, and it would have a default subnet mask of the same. This tells the router that it doesn't know where to send it, and it doesn't know what network it belongs to. So it'll use its WAN gateway address of 76.30.4.1. So you see, it's really all just about decisions. If the router knows, and by knowing it would be in the routing table, the destination IP, it simply forwards that packet on. If it doesn't, it will send it out its default gateway. So understand that every node on the network has a routing table, and it goes through a similar decision process, whether to send it directly to a host on the LAN or to send it through a default gateway to a host on another LAN. So when making these decisions, they're all based on relative cost. So the relative value of a route is called the cost. When more than one route to a destination is available, the lower metric is used. When the route with the lower metric goes down, then an alternate route will be used. So here we see the routing table on a Windows XP machine. The way this works is Windows machines read from the bottom up, going through all local addresses before going out to the router. For the broadcast address, occasionally your computer needs to send a broadcast to other computers on the same network. For that, they need to know the network ID. The difference between a direct broadcast and a full broadcast is a direct broadcast goes only to the targeted subnet, not the full broadcast domain. The NIC is the gateway between the local PC and the destination. So it'll just pass it out to the NIC and the destination will get it. Anything that's not local goes to the router and from there out to the desired destination. To look at a computer's routing table, open up a command prompt and for XP and Vista, just type in route print. Now understand there's a difference between the two. In XP, the gateway for the local destination is shown as the local NIC IP, whereas in Vista, the gateway is shown as OnLink. Here's a look at a Windows Vista routing table. So as I mentioned, routers operate at layer 3. There is a relative freedom from the layer 2 confines. Routers connect different network technologies, and the only way to do this is they have to strip off all layer 2 data. Being free from the layer 2 confines means that routers can connect almost anything that stores an IP packet, even non-Ethernet network technologies like frame relay and ATM. So for commercial grade routers, many of them give you the possibility of adding additional ports. For instance, Cisco routers come with removable modules. This allows you to connect, for instance, a Ethernet network to an ATM. Next, we'll talk about NATing, or Network Address Translation. NATing enables routers to hide IP addresses from the internet. Also, because of the scarcity of IPv4 addressing, it allows us to conserve IP addresses. Before NATing, you would acquire a block of unique IP addresses from your ISP, and then you would assign those IP addresses to each computer and to the LAN connection on the router. Next, you would need to assign the IP addresses of the ISP's router to the WAN connection on your local router. Then give all the LAN hosts the IP address of that gateway router. So with NATing, you have choices. Either basic NAT, you might also see it called PAT, which would be port address translation. The NAT capable router replaces the source IP address of a LAN computer with the source IP address of the router's WAN connection. Then the LAN uses a private IP address, something either in the 10 dot or 172 or 198 range. This differs slightly from traditional NATing, where you would take your source address and then NAT it, or your destination address and then NAT that. We would have to deal with things called static NAT and dynamic NAT. These are all things that you should know. However, most modern routers do this automatically. So when we add ports to the mix, the TCP/IP involves more than just the IP addresses. The NAT uses the TCP/IP port numbers along with the IP addresses. This solves a very important security problem, as well as alleviate the issue with the scarcity of IPv4 addressing. This creates a new kind of port. Remember, TCP/IP ports are 16-bit numbers. They range from 0 to 65,535. All packets contain port numbers. It determines the type of session and software that you use. When dealing with these ports, you'll have two options, either the destination port or the ephemeral port. The destination ports are fixed, they're predetermined numbers. The most common range are 0 through 1023. Ephemeral ports are an arbitrary number generated by the sending computer. The receiving computer uses this as its destination address. The most common range of the ephemeral ports are 1024 through 5000. Next, we'll talk briefly about overloaded NAT. Overloaded NAT is simply when a single public IP address is being shared by a number of computers. Computers normally share a network ID. They also normally will use a private IP address on its own local LAN. This is padding, or port address translations. It handles the one-to-many type connections. It uses port numbers to map traffic from specific machines on the network. It also changes the private source address and port number to something usable on the internet. The original address and port number are recorded in the PAT translation table and swapped for a new one that is used on the internet. This way, it knows when return traffic destined for the original host machine, it can swap that information back so that it arrives safely. Similar to PAT is port forwarding. This hides a port number from the internet. It enables public servers to work behind a NAT router and gives the server the protection of NAT while allowing access to the local server via the internet. So a web server behind a NAT router, that router recognizes all incoming requests on a given destination port. It then forwards that request to an internal IP address. For instance, if the router is configured to forward all port 8080 packets to the internal web server on port 80. So bear in mind that some manufacturers use port forwarding to mean the same as overloaded NAT or PAT. However, Cisco uses the term PAT to refer to overloaded NAT. As long as you understand the basics, you'll be just fine. To configure NAT, it's pretty easy on home routers because they often have NAT turned on by default. Usually, you'll just start by selecting the type of NAT that you want, whether it's pooled NAT or port forwarding or any other combination. Next, we'll talk about routing, more specifically, dynamic routing. So understand, we've talked about the routing table in your routers, and all routers have what's called static routes. These can either be manually configured or auto-detected at setup on the router. With dynamic routing, now there's different protocols involved. Routers communicate among themselves with change information. They update each other on changes about direct connections and the distance to the next router. So to understand these hops, we need to understand the routing metric. Routing tables contain criteria called a metric. It's a relative value that the router uses when there is more than one route to another network. We've already spoken about this. These metrics determine which route the router will use. It will always select the lower value metric first. To determine which is the lowest value, different route protocols use different metrics and ways of calculating them. Some will calculate with MTUs, or maximum transmission units. These describe the largest frame a particular technology can handle, for instance. Or others will use a hop count. These are the number of hops to the next router between two networks. Depending on which technology they use, whether it be MTUs or hops, another piece that goes into the calculation is the relative cost, bandwidth, and latency. Now that you understand the basics of dynamic routing, now we'll break it down even farther, starting with distance vector. It was the first type of dynamic routing protocol, and pretty much the cornerstone of distance vector routing is total cost. To determine the total cost, it really is as simple as adding up the amount of hops. However, the problem with distance vector routing is it only relies on a simple hop count. It doesn't take into account the speed differences of other routes. So administrators set metric values higher on slower routes. This can be somewhat labor intensive on a larger network. Also, with distance vector routing protocols, you need to calculate the total cost of a network ID. Compare that total cost to all other possible routes to the same destination, and then select a route with the lowest cost. So what happens if there's more than one route to the same destination? Well, if there are multiple routes, the router will only keep the lowest cost route, and then it will delete all others. The next issue that we need to deal with is a term called convergence. This is the point at which the updating of routing tables is complete for all routers. If a low-cost link breaks, the router can no longer send to that destination network ID until several iterations of updating included the slower. Also, with convergence, distance vector routing protocols work only for fewer than 10 routers. Probably one of the most common distance vector routing protocols would be RIP. Starting with RIP version 1, it has a maximum hop count of 15. The routing table requests could loop all the way back to the initial router. Within RIP version 1, every router updated every 30 seconds. This caused a huge network overload. And only routed classful subnets. It didn't work with VLSM, or variable length subnet masking. And since there was no authorization with RIP, it left routers open to hackers sending false routing table information. So enter RIP version 2. It fixed many of the problems from RIP version 1, like now the availability of VLSM, and updates are sent at random intervals instead of every 30 seconds. However, RIP version 2 is only really suitable for smaller networks. It still has a 15 hop count limit and still has time to convergence problems on larger WANs. Next, we have BGP. With the explosive growth of the internet in the 80s, it led to changes initiated through the internet governing entities like the Internet Society, IANA, and IETF. This led to a reorganization of the internet into a multi-tiered structure. It introduced concepts and terms like autonomous systems. An autonomous system is simply with one or more routing domains that are governed by a single dynamic routing protocol. Autonomous systems do not use IP addresses, but globally unique autonomous system numbers, or ASNs. These are assigned by IANA. So the way BGP works, it uses the autonomous systems to communicate with each other using an exterior gateway protocol, or EGP. The network or networks within the autonomous systems communicate with an interior gateway protocol, or IGPs. Neither of these are dynamic routing protocols per se. So with this, many protocols that are used within the autonomous system, such as RIP, the internet uses one protocol for communication between the autonomous systems, and that protocol is BGP, or the Border Gateway Protocol. An important note here is that CompTIA lists BGP as a distance vector routing protocol, but BGP really is rather different. With BGP, it has different types of routing tables. The BGP routers are manually configured to know each other, and they advertise information that is passed off to them from other autonomous systems' edge routers. Now, an edge router is simply a router that performs AS to AS communications for its own autonomous system. BGP forwards advertisements that include the autonomous system number and other non-IP information. BGP is capable of handling tasks that are exclusively unique to the internet. Most BGP routers will ignore unreliable routes. With BGP, it supports policies that ISPs can use to limit who and how other routers may access them, and true BGP knowledge is really only needed by the few people who work with routers belonging to the autonomous system on the internet. After distance vector routing, we deal with link state routing. This is another dynamic routing protocol that announces and forwards individual route changes as they occur. Only two link state dynamic routing protocols are used. They are OSPF and ISIS. With OSPFs, or Open Shortest Path First, it is the most commonly used internet gateway protocol in the entire internet. It's designed to work within a single autonomous system. It's a fairly complex routing protocol, so you generally will only find these on commercial grade routers, not necessarily in the less expensive home routers. With newer OSPF capable routers, they send out link state advertisements. These are also called hello packets. It sends out lots of LSA hellos on first boot, basically flooding the line, and then only periodically thereafter. This is so that it can advertise itself, if you will, to the rest of the routers to know that there is another link that is available to route traffic. So, unlike the distance vector protocols, OSPF bases costs of the route on the speed of the link using a basic formula. Essentially, the faster the link, the lower the cost. Now, you can override this manually if you so choose. OSPF routers exchange information and update their link states in databases. The hellos forward to every OSPF router known to each other. Within a few seconds, every router knows the link state of another router. Within the OSPF architecture, each router is then assigned an area ID. The area ID looks exactly like an IP address. For instance, the area ID assigned to the backbone would be 0.0.0.0. So within OSPF, you have elections. With these elections are selected designated routers. There is one for each area of the OSPF architecture, and it relays information to all other routers that it is the designated router. With each designated router, there is a backup designated router. So if the designated router ever goes down, the backup simply picks up. So as I mentioned, this happens during an election. It occurs during the initial hello when an OSPF router is first initialized. The router with the lowest total priority will win the election. However, like I said, you can manually manipulate which router is the designated router or which router will be the backup designated router. However, it is best to let the routers select the winner of each election. After the election, the routes are distributed across the area. Each router sends an LSA telling other routers on the area in the network IDs as to who won. OSPF areas achieve convergence almost instantly compared to RIP distance vector routing protocols. So after convergence, each router in the area sends hello LSAs about every 30 minutes or so. With OSPF routers, they also keep an alternate route with the same network ID. They do this in case something changes. For instance, if a link breaks between, let's say, router A and router B, routers A and B almost instantly can detect that break, and then each router, after they attempt to reconnect, after a few seconds of failure, the router sends out an LSA announcing the broken link. However, instead of sending the entire table, it will only send a change to that link. So this way, all other routers will only have to update the single change without having to worry about accepting an entirely new routing table. With the introduction of OSPF, it is widely popular. Most people kind of took to it immediately, mainly because it's extremely easy to use. It scales extremely well with large networks. However, until recently, OSPF was not capable of supporting IP version 6. Next, we'll discuss ISIS, or Intermediate System to Intermediate System. It's the only other link state dynamic routing protocol. It operates similar to OSPF, and it uses the same concept of areas. With ISIS, it sends only updates to routing tables. It was developed around the same time as OSPF. However, it does work and has worked with IP version 6 from the start. Some ISPs use it, but ISIS is still primarily used as a distant second to OSPF. Now, I did say that there were only two. However, there is a third that you should know about. EIGRP, Enhanced Interior Gateway Routing Protocol. It is a Cisco proprietary, so you have to be using Cisco gear to do it. But it really doesn't fit in either category. It's neither distance vector nor link state. It's really a hybrid of the two. It was developed to replace RIP and was introduced before OSPF. Dynamic routing really makes the internet work. The internet depends on dynamic routing for self-healing. Manual updating is impossible with such a wide internetwork of computers because there are many routes that are coming up and down almost every second. The Network Plus expects you to know and understand the different types of dynamic routing protocols. Here's a chart for you to help keep them straight. Routers, by and large, whether they're home class or business class, the physical installation is really pretty simple. With a home router, simply give it power and plug in the connections. A business class router, well, you'll insert it into the rack, give it power, and plug in the connections. However, this is about where the similarities end. Each router must be configured, that's true. You'll use what's called a Yoast cable. It's the oldest method for connecting a router for configuration, almost unique to Cisco brand routers as well. You might also hear these referred to as a rollover cable. Here's a picture of a Yoast cable or a Cisco console cable. You'll use the console cable to connect to the router. They're managed devices that include both routers and some of the newer advanced switches that can be configured. Plug the rollover cable into the console port of the Cisco router, and then plug the other end into the serial port of a PC. However, as you can imagine, with most modern PCs, you may need to use a USB to serial adapter. The console port on the router is marked console, and it's somewhat color-coded. It usually is the same color as the Cisco console cable, a light blue. Next, you'll need to use some sort of terminal emulation program. The most popular would be PuTTY. However, you can do this through the hyperterminal. You'll need to configure the serial port settings. It is somewhat specific. You'll need to set them at 9600 baud, 8 data bits, and 1 stop bit with no parity. Here's a look at a configuration in PuTTY. Once connected and running the terminal emulator, you will see the initial router prompt. On a Cisco router, this is the Cisco IOS prompt. You'll type enable and then press enter. You'll notice that the prompt changes to router. Understand that the Cisco IOS is a fairly complex IOS and takes specialized training to understand all the nuances of it. However, newer Cisco routers will lead you through at least the initial configuration and the basic setup. Here's a look at the initial router prompt of a Cisco router. More and more routers, even the business class routers today, allow for an easier web access for access and configuration. Most routers even have a built-in web server where you can do just about everything you need to. It is a whole lot easier than working with the Cisco command line iOS, and the web access only works if the router has a built-in IP address from the factory. Otherwise, you'll need to enable the web interface after assigning an IP address via the command line interface. While most techs will use a laptop and a special cable like the rollover cable to connect directly to the router for its initial configuration, after the basic setup, most will then switch to the web-enabled interface. Whether you're using a console cable or the web access, it is important to check the link lights to verify that you have made proper connection, and then open up the web browser and enter the router's IP address. You'll also need to enter the default username and password. You'll find that in the router's documentation. And then, once logged in, you'll find all the appropriate settings that you need. So to manage your routers, administrators need more advanced tools than the simple web server on a router. For this, you'll revert to the network management software. It includes utilities that will allow you to manage the entire network in a single interface, whether it be routers, switches, or even computers. The network management software is often a website, and administrators manage the network and make necessary changes from it. Often they are proprietary tools depending on the manufacturer. However, they're usually very powerful and easy to use. Here's a look at Cisco's Network Assistant. Now, when it comes to network management software, there are several to choose from. There's a lot of third-party software tools out there, some of them even free. But those are usually harder to configure and must constantly be updated to work with as many devices as possible. So, whenever possible, you should use the network management software that is unique to the type of devices that you wish to manage. An example of this is Cisco Works enables you to change the IP address of a port where third-party tools will only let you see the IP settings. One popular third-party network management software tool is called Open Network Management Software. It is open source, so it is free to use. However, it can be a little cumbersome to administer and set up. Now, understand that routers have more than one way to connect. For instance, your home router may come with a USB port as well as configuration software. More powerful routers may allow connection via a telnet protocol or secure shell. So, no matter what you use, understand that there are more than one way to administer your routers, and which you choose is less important than how you choose to administer them. We'll take a closer look at some of these terminal emulators in a later module. So to perform basic router configuration, you must have at least two connections. You must properly configure every port on the router to talk to connected network identifiers. And then make sure the routing table sends packets to where you want them to go. The first step would be to set up the WAN side. The WAN side in home or small business routers connect you to the ISP. You'll usually get this setup information from the ISP itself. Most home routers are going to use DHCP on the WAN side, and all you need to do is just plug it in and wait for the configuration to complete. However, you may need to enter a static IP address. You can buy a single static IP from an ISP, and if you do have a static IP address, your ISP will tell you what to enter into the router's interface. Next, you'll need to set up your LAN side. You'll usually have total control over the LAN side. You'll choose your network ID from a private range, whether it be 72 or 198 or 10, and then assign the correct IP information to the LAN side NIC. Next, you'll need to establish your routes. The router will usually build a routing table based on information you provide. Of course, you may need to add more routes later. To do this with a business class router, you'll have to do it in the iOS command line on Cisco routers. And next, and this is completely optional, you'll configure a dynamic protocol. Remember, dynamic routing protocols are tied to the individual NICs. When you connect two routers together, make sure the NICs are configured to use the same dynamic routing protocol. Once the dynamic routing protocol is turned on, well, the rest of it from there is automatic. And the last step, and probably the most important, is to document everything you've done and back up your configuration. This way, if anything happens, you can simply reload the backup without having to go through the entire setup process again. When troubleshooting routers, it's always best to consider non-routing issues first, because routers don't usually fail. You'll want to check the NIC, check the computers, and check the switch before diving in and thinking it's a router problem. Routers really are more reliable than any other equipment on the network. Keep in mind that what your router is supposed to do is route traffic. If traffic is being routed, then it's not a routing problem. However, it is important to know how to use a few basic tools that can help you check for any routing problems that may be occurring. One of those would be traceroute. With traceroute, kind of like ping, it records the route between any two hosts. However, unlike ping, it will return information about every router between them. In Windows, you'll simply type TRACERT. In Unix or Linux, you'll type TRACEROUTE, or you might possibly have to put a my in front of it. Well, there you have it. Pretty simple, right? I know, it can be a lot of information coming at you all at once, but don't worry, I'm here to guide you every step of the way. You can do this. Just remember, study hard, lots of practice questions, and you will succeed. You will become a Network Plus certified technician. I'll see you next time.